Hi everyone, I'm Taekyung Lee, and this is the joint work with Mr. Darwin Mick and Professor Howie Joseph from the CMU Robotics Lab, done through the Robotics Institute Summer Scholars Program. Today, I'll talk about how to make the multi-robot search safe and effective when adversaries are actively trying to disrupt it, and importantly, when nobody has perfect information about where anyone is. Here's the motivating scenario. A humanitarian robotic demining. Right now, about 20% of Ukraine is contaminated with unexploded ordnance, and robots are a natural fit for clearing it. And the prior work has looked at this as purely as a coverage problem, sweeping an area effectively. But what happens if their adversary is actively trying to stop from demining robots? That changes everything. Now, the robots can't just plan the most efficient sweep, they also have to survive. You can see this in the cartoon, where the agents start out searching freely, but once adversaries engage, some agents get pursued, and one gets captured and drops out. And interestingly, the remaining agent naturally shifts to cover more ground on its own. But nobody explicitly told it to do that, it just emerges from the game. And this is a phenomenon we want to capture formally. So we model this as a differential gain. Agents minimize a cost that combines three things: an ergodicity term that rewards good spatial coverage of the information map, a term that rewards distance from the nearest adversary, and a control effort penalty. Adversaries, on the other hand, have a much simpler objective, which is to minimize distance to whichever agent they're pursuing, plus their own control penalty. Both teams share the same underlying dynamics, same state, same physics, and they have an opposing objectives. And this asymmetry, which the agents are balancing search and survival while adversaries are only caring about pursuit, is what makes this general sum game rather than a simple zero sum pursuit evasion game. This game formulation itself comes from our prior work published in the IEEE Control Systems Letters. The paper solves the game, but it has two limitations. It assumes perfect information. Every player knows exactly where everyone else is, and it solved the game with simultaneous gradient descent, which is slow and gives only weak asymptotic guarantees about reaching a Nash equilibrium. Our goal in this work is to instead pose this problem as a linear quadratic differential game, or an LQDG. Why? Because LQDGs have closed form Riccati based solutions that provably reach a Nash equilibrium. No slow iterative gradient descent is needed. If we can get our problem into that form, we can get the exact equilibria essentially for free. Here's a catch. The Riccati-based LQDG solvers require the cost to be in what's called a Boltzmann form, a terminal cost plus a running cost that only depends on the state and the control at each individual time step. Now look at our agent cost function. The ergodicity term depends on the agent's time average trajectory statistics over the entire horizon. So it can't be broken down into time step by time step. So our cost simply isn't in Volta form, and the classical closed form Riccati machinery doesn't directly apply. So that's a core technical obstacle this paper solves. Our solution is the projection-based trajectory optimization. The idea is that we start with some initial guess for all the players' trajectories, and this guess doesn't even need to be a dynamically feasible. When then we then project these infeasible trajectories onto the manifold of trajectories that actually satisfy the system dynamics. Then instead of optimizing over that curved manifold directly, we linearize around the current point and solve for a descent direction in the tangent space. And it turns out that it is the tangent space, the problem is linear quadratic and it's in Volta form, even though the original problem wasn't. So we can apply the Newton's method with a coupled Riccati recursion to get the equilibrium state. Take that step and reproject back into the feasible manifold and repeat. This coverage converges into a trajectory that is both dynamically feasible and a local open loop Nash equilibrium of an original game, with a formal proof backing that up, which is provided in the paper. That solves the perfect information version, but real contested environments don't give you perfect information, and each robot only gets noisy local observations of everyone else. So we reframe this as a partially observable stochastic game, or POSG, and turn to a multi-agent reinforcement learning especially MAPPO, which naturally handles uncertainty. We use the classical centralized training, decentralized execution setup. During tip training, a centralized critic sees the global state, but actually in the deployed policies, the actors only ever see their own local and noisy observations. That's what lets this transfer to real decentralized robots. But there's a subtlety. MAPPO alone gives you no guarantee of converging to a national equilibrium. In general sum games, standard policy gradients can just cycle forever. Prior work by Lee et al. Addresses this with the multi-agent guided policy search, or what we call MAGPS. Instead of randomly sampling player actions during training, you bias samples toward a pre-computed Nash equilibrium. So our goal becomes is to use the MAGPS algorithm to learn policies that are both robust to observation uncertainty and anchored to a real Nash equilibrium. Here's how it all fits together. On the centralized training side, our projection-based Riccati solver from the few slides ago runs on a global state to compute on exact local Nash equilibrium of each training step. That equilibrium becomes a guidance signal that regularizes the actor updates, which pulls each agent's and adversary's policy toward the equilibrium action. Meanwhile, the actors themselves are only ever trained and evaluated on local and noisy observations. So at deployment, we throw away the solver and the critics entirely so that the robots just run their lightweight actor networks on local sensing. So how does this perform? So first, we look at the parity engagements, equal numbers of agents and adversaries, scale from 1 versus 1 all the way to 10 versus 10. On the right, the top plot shows spectral ergodic error and the time to capture across three controllers, the ILQR or the receding horizon controller solver with perfect information, the same receding horizon controller solver but with the imperfect noisy information, and our MAGPS guided policy, RL policy. The learned policy tracks the imperfect information solver reasonably closely in coverage and quality and survival. Well, the bottom plot shows the real payoff, which is the MAGPS's compute time barely grows with team size, while the LQR solver's compute time um, is relatively uh, two times more higher. That's a practical benefit of learning the policy instead of the solving the Riccati recursion online every step. Next, we look at the asymmetric team sizes: three agents versus one adversary, two versus two, and one versus three. This lets us see the immersion division of labor of behavior directly. When agents outnumber adversaries, one agent effectively absorbs the adversary's attention or gets captured, freeing the rest of the team to search unopposed. Exactly the behavior we saw in the motivating cartoon that in the beginning. As the numbers flip in the adversary's favor, agents are forced into much more defensive and evasive behavior at the cost of the coverage. We also checked robustness across dynamics models: double integrator, point mass, kinematic unicycle, and kinematic bicycle. Under both the projection-based receding horizon controller solver, or the LQR, and the MAGPS solver. The qualitative behavior holds up across all four, which is that the agents still evade adversaries and prioritize high information regions, regardless of the underlying dynamics model. This matters because it means our framework isn't tied up to one specific robotic platform and it generalizes across how robots actually move. And finally, we validated this on real hardware, which we ran a two versus two engagement using a physical turtlebot platform robots, uh, tracking with RViz, and executing a decentralized MAGPS policy in real time. The trajectories you see on the right mirror what we saw in the simulation, which is the agents weaving around the adversaries while still concentrating time in high information regions, which gives us confidence that this isn't just a simulation artifact and it transfers into real robotic hardware with real sensing noise and real dynamics. A few open directions to close on. Right now, our methods don't account for obstacles at all. A natural first step in deploying control is controlled barrier functions, but naively filtering the executed control breaks our natural equilibrium guarantee. So the real fix is to formally extend this to a generalized Nash equilibrium, or a GNE, via a constraint formulation with the augmented KKT conditions. We're also interested in beliefs-based planning and policy estimation to handle line of sight restrictions, since obstacles don't just block motion, they also block observations too. Thank you so much.